So last class, we were working on MNIST. Remember, the MNIST data set is this data set of pictures of digits, like low resolution pictures of digits. This is what they look like. They're 28 by 28 pixels. We were thinking of these, we unwrapped them into one big long vector of size 784. And so there's a vector of 784 that tells you the color of the pixels. So the first pixel, the second pixel, the third pixel, and so on. And there's one label. The label is either 0, 1, 2, 3, all the way up to 9. And here are some examples with their labels. Very nice. We first did this by linear regression, but we didn't just say scikit-learn linear regression. We did it from scratch using neural networks and the gradient descent algorithm. So what does that mean? Well, we started with random parameters. So we had this thing that just started the parameters out purely at random. And then we fed those parameters in to a dot product to get the output. So linear regression is just doing a dot product between the weights W and the image X. Let me zoom in maybe a little bit more so you can see it. This is what we filled in last class. That was this picture. Ooh, let's see if I can get the board from last class. The board from last class was this one. Okay. And this should be way, way up here. Yeah. Okay. So we were combining the x's, which are kind of the values of these circles. These circles are called neurons sometimes. So we start the input with the values of every pixel. We multiply by these edge weights, which we call W in green. And we did x1 times W1 plus x2 times W2, all the way to x784 times W784. They get added together, and that was the output. That's what linear regression is. Okay, very nice. And the problem with this thing was we measured how good it was doing with mean squared error, which we also filled in. And then we did gradient descent. So we tried to improve the mean squared error by adjusting the parameters in the direction of the gradient. That was this thing over here. So the W's, they move in the direction of the gradient, dW. They go down, that's the minus sign. And they move, how much do they move? They move this thing called step size. We saw that if the step size is not right, things won't work either. Okay, then we have this training loop. The training loop goes through all the data and finds the gradient with the JAX.grad, which is this amazing function that can find the gradient of a computer function. And then it adjusts it a bunch of times, and we had these little runs like this. So we ran through all of the examples, that's an epoch, and it took 10 seconds. Our training loss was 126. Then we ran through all the examples again adjusting the parameters every time, and our training loss was 90. This is the square loss. So if the square loss is 90, then the root mean squared loss is what, like 9 or 10? Somewhere between 9 and 10. The reason it has to be the mean squared loss, if you put the root in front of it, it changes the derivative by this annoying amount. So this is one situation where you want the mean squared loss and not the root mean squared loss. Maybe you could have the root right before you print it, but the function needs to be the mean squared loss, or the derivative won't be as nice. Okay, and then we plotted these, and these were the first few examples and our prediction. So this is this digit over here, drawn with pixels. We predicted it was a -6. This one we predicted it was a -10. These are some bad, not great predictions. Did we get any of them close? Hey, the closest thing we got is this one. We had it suspiciously close to pi, 3.149. Okay. Okay. And then we were like, hey, this is actually really silly because linear regression can output any number between negative and infinity. Our numbers are between 0 and 9. So let's do it by applying a sigmoid. So we applied a sigmoid to the output. Instead of doing just the dot product, we did the sigmoid of the dot product. And that crunches all the numbers. Instead of being between negative and infinity, now they're between 0 and 1. And then we're like, wait, we don't want 0 and 1, we want 0 to 9. So we multiplied it by 9. This was all last class. And that was our output between 0 and 9. And this worked a lot better. So we did this. And the mean squared error, look, if you have I think when I did it before, I didn't have the step size quite right, or the scale. But if you do it with the correct step size and scale, and it's working, you get an error of like 3. So the mean squared error is like 3 with this approach. A mean squared error of 3 means you're off by like 1 or 2, typically, right? The square root of 3 is somewhere between 1 and 2. And so here are some examples. This digit we thought was a 2. This digit we thought was a 3.97. This one we thought was a 1.95. And look, this one we thought was a 7.76. So, pretty close. Like we were off by like 1 or 2 every time. So that's the neural network working. That was all stuff we did last class. Okay. Any questions or comments about this stuff, or like how the neural network works from last class that we did? Okay, so that was all stuff we did. Then at the very end, we said, wait a minute, this is all very silly. This is not the right way to do this problem. In fact, we were doing all this to learn how the neural network works and learn the basics of it. But we made a fundamental mistake. A fundamental thing we did, if you submitted this, any reasonable person would go, why on earth are you doing it as this? What is the thing that we're doing wrong that's silly up until now? Nobody wants to answer, so I will make a mathematized question and force you to answer. This is the thing I can do on mathematized. So we're going to close this thing, and we're going to just make a new question called create exercise. Oh, we can do a word cloud. Let's do a word cloud. What is wrong with this approach? I think we did this also last class. Maybe you are shy to answer, but this way nobody can hide. You must answer. All right, what did we do? What did we do that was silly? Okay, so like 10 seconds left. There's a few people still getting their answers in. Let's see, 2. Okay, time is up. I think we're just getting everybody here. Should be an easy question if you're awake and we're here on Wednesday. What do people say? Word cloud. All right, amazing. I see the big words that I like, classification and regression. That is exactly what's going on. Lots of people. 8 people do not know. If you do not know, you need to revisit the very basics that we learned right at the beginning of the course. Same with, lots of people. Actually, like half the people put in, they don't know. And let me see, 8, 9, 10, 11. This is not right, 12. This is not right, 13. This is not right. Okay, 1, 2, how many people got it? This one, there was one up here. This is perfect. 3. Okay, lots of people got this at the end here. Okay, good. Thank goodness. 4, 5, 6. Okay, so maybe like a quarter of the people put in an answer that is reasonable. The thing that we are doing wrong, that you can see, is that we are making predictions that are not integers. Where did it go? Right? Why on earth would you estimate this is a 1.95? Doesn't make any sense. If someone shows you this, you should get angry. You should go, what are you talking about, man? 1.96. It's a digit. It's not a decimal. We're not doing decimals here. What digit is it? You should at least like round this off or something, like if you want to do it this way. But actually, the way we're doing it is not right. We should be doing classification. We should be doing classification. And that is what we actually, talked about this on Wednesday. We got to the classification, right? And we said we should actually not have one output. We should have 10 outputs. Our network, at the end of the network, we should not read off just a single number of what is the digit. We should read off 10 numbers, which is it class 0, is it class 1, all the way up to is it class 9. And those 10 numbers we will then convert into probabilities, and those probabilities we will then use to measure how good or bad we are doing, how close we are. Okay. And last class, we talked about the sigmoid. We did a lot of sigmoids when we were doing binary classification. When there are 2 classes, then we use the sigmoid. But now we have 10 classes. So what do we have to do? Well, we have to convert the logits into the probabilities. So these numbers are called logits. They're numbers between, these are logits, and they are numbers between negative infinity and infinity. And we must convert them into probabilities. Convert to probabilities. We did this in class a while ago. We talked about it a little bit on Wednesday. We said you can't just apply the sigmoid function because then they do not add up to 1. You have to do something else, something called the softmax. And this softmax function is like a workhorse of machine learning. And it essentially is this question: how do you convert the logits into probabilities? And I have a mathematized for you to try it out. Let's see if we can get it. Logits to probabilities. You're working on a classification algorithm. For this particular example, your algorithm thinks the logits for class 1 and class 2, class 3, there's 3 classes in this example, are 1.5, -2, and 3. Which of these formulas is the correct way to convert this into the probability for class number 2? So in other words, if your network outputs 1.5, -2, and 3, how do you interpret the probability that it is a class 2? It is probably class 2. Okay, and I have 4 options for you. Think about what they are and which one's right. Maybe flip through your notes and try to do this one. Okay, let me give you a few minutes. All right, there's like 20 seconds left. I'll give you a couple seconds after, but put it in your gas. We'll see if there's a consensus. We'll know we have it. If there isn't, we'll do a revote and try to make it work. All right, let's take a look. What did people do? Drumroll, drumroll, drumroll. Okay. Nobody fell for e to the -2. That's great. 2 people fell for just apply the sigmoid, which is the thing I said, don't do that. Right? I said, don't just do the sigmoid of -2, because then it doesn't add up to 1, which leaves us with these 2 options. And the way you can tell which one it is they should add up to 1. And 16 people correctly figured out that if you do it this way, it adds up to 1. The other classes would be the other things in the denominator, right? So the probability of the first class would be e to the 1.5 divided by that stuff. The probability of the third class would be e to the 3 divided by that stuff. So when you add it up, the numerator and the denominator are the same, and it adds up to 100%. So that is exactly the softmax function, which is converting logits to probabilities. So the softmax of logit 1, logit 2, ... all the way up to logit n is equal. You do this function e to the logit 1 divided by the sum logit 1 plus e to the logit 2 plus ... e to the logit n. And then you do this whole thing. You just change what's in the numerator for each of them. Okay. Right? That's what it is. So it's the vector, and it turns these into probabilities. These are now probabilities. This is p, I'm going to call them p hats, p hat 1 all the way up to p hat n, where n is the number of classes you have. Okay, very nice. So now we're going to do this in our code, and we just have to fill in what to do. All right, MNIST example with blanks. just type in what we just did. We want the one with the second half blank. This is what we were working on. Let's close that so we don't get confused. Okay, logistic regression, got the logits. Okay, here is one little difference. I have the formula for the probabilities written, but the code is asking me for the log probabilities. So in other words, don't calculate the probability, calculate the log probability. And we're going to see that in a second. We actually don't need the probability, we need the log of the probability. So it's easier to just calculate it here rather than calculate it and then do the log. So I just have to do one little thing. These are the probabilities. What are the log probabilities? So I got to do the log of the probabilities. Okay, and so that's the log. The log here is the natural log. Let me write ln so there's no confusion. Ln, the natural log. Who came up with this stuff? Okay, so it's the log of e to the logit. Let's do it with class 1 just for funsies. E to the logit 1 plus ... plus e to the logit n. Okay, and the nice thing about the log is when you divide things, the logs subtract. So you end up with the log of the top, e to the logit 1, minus the log of all the stuff on the bottom, e to the logit 1 plus ... plus e to the logit n. And now something else happens. You have the natural log of e to the something, then they cancel out. Okay, so you get the logit 1 minus the log e to the logit 1 plus ... plus e to the logit n. I call this thing sometimes the log sum exp, because you first apply the exponential function, then you add them all up, and then you take the log. And by doing the log sum exp, basically the log probabilities are the logits, but shifted over so that they add up to 1. This is the thing. So the log, you could say this as a quote, the log probs are the logits minus the rate constant. Let's say the correct constant. So they sum. They sum to 1. Let's say the probability sum to 1, because it's not the log probabilities. It's sum to 1. It's the probabilities. So the probabilities sum to 1. So in other words, the log probabilities are the same as the logits, just shifted. So in the example I did, where I had a -2 and a 1.5, they're going to get shifted up and down by the same amount. The relative ratio between class 1 and class 2 will always be the 1.5 to the -2. So that's very nice. Okay, so how do we do this in the code? We do the log probability. So I have to do the log sum exp of the logits. So I'm going to do the logits minus, and then I'm going to do the log sum exp. Oh, look, here. Google suggested this to me. See, Google knows what I'm doing. That's because all these things are very standard. So when you name your random variable, or you name your variable log p, and you name your thing logits, then Google says, hey, they're probably going to do the log sum exp. And indeed, that's what I want to do. Let me type it out, though, because I do want to do one thing. jnp.sum jnp.exp of the logits. Now, I have put it in the wrong spot. Okay, yeah. Okay. jnp.logits. Okay, there we go. All right. So that's perfectly correct. And you run it, and it should work, and everything should be fine. What is it complaining about? Did I have to? Oh, I never closed it. I deleted a bracket. Okay, that's good to know. Let's put this back here. Oh, I typed logits up here. I see. Okay, well, let's not worry about that for now. Okay. Now what do you not like? Oh, I didn't put in the shape correctly. Remember, the output size, we did this last class, should it be 10? Because there's 10 classes. Okay. Now everything should work. Okay. Okay. And if I run it now, I get some predictions. So I ran this on an example, and I got these 10 numbers. The log probabilities are -5, -1.6, -0.2, -74, and so on. These are the log probabilities. If I run the log probabilities, I can also get the probabilities by doing the exponential. So let's do that. So this is the log probabilities. I'm going to do the actual probabilities by doing the exponential. So let's just add an exponential, jnp.exp, and then I will tack that on. Okay. So these were the log probabilities, and then I took the exponential, and now they're actual probabilities. You see they all end with e minus 3, so this is 2 to the times 10 to the minus 3. This is 1.8 times 10 to the minus 1. The largest one is this one. This has the biggest log probability, negative 0.2, which is an 80% chance. So the computer thinks there's an 80% chance that this image is a class 3. Class 3 is actually the digit 2, because it starts at 0. So 0, 1, 2. So this, we think this thing is a digit 2. Okay, that's implementing logistic regression, and the softmax function is used in machine learning all the time, so it's a good one to understand. Are there any questions or comments about how that was implemented? What we did? Okay, next up, we need to measure how good or bad our solution is. Oh, let's go back. I'm going to do one little computational thing. You might have noticed this line. The Logits max is 0. So remember, the only thing that matters between the Logits is their relative values. It turns out if you have really big Logits, like if your Logit is 100, then your computer will try to do e to the 100, and then it'll explode and be really sad. So by doing the Logits max 0, you subtract the maximum value. You keep the relative values the same, but you make sure that you never have big numbers. And when you never have big numbers, you'll have less computer problems. So it's a little bit better to do the Logits max 0. This is the same exact output. So it should be exactly the same. Oh yeah, I guess they're random numbers. So the numbers came out differently. Oh, something is blowing up, because these aren't Logits anymore. What did we do wrong? Logits max 0. Oh, okay. When you subtract, you can't do the Logits minus that. You got to do the Logits max 0. Now it will be the same. Okay. So we just added a constant everywhere. And now, yeah, look, it's exactly the same. It's just that we avoid these large numbers that can blow up the computer that will mess things up. Okay, so we're done with that. The next question that we have to ask ourselves, and this is, again, core, absolute staple of the course and what we're doing with our lives, how do we measure how good or bad a prediction is? How do we measure how good / bad a predicted class is? Okay? Absolutely essential. If you don't have a good handle on this kind of thing, if you are running in automatic mode and you don't worry about this issue, then you have not understood data science. This is what, like the core element of the course, we have a method to measure by how good or bad our predictions are, and we optimize according to that. What is the method to do this? What are we doing? And I have the mathematize here to let you tell me how much you know or don't know. Actually, okay, why don't I like the word clouds. Let's do a word cloud. How do we measure how good or bad our predictions are? Okay, remember, we are doing classes here. Okay, that's live, or it should be live. Do we have to press a button? Did it explode? Oh, okay, start. Okay, we're gonna start with the words, and then we'll get into math. Okay, just a few more seconds. I guess most people are already in. Okay. Did it go away? Okay. What did people say? Oh my goodness. Ho, good. We got some nice text here. Ready. Mean squared error. 2 people said mean squared error. The answer is not mean squared error. Mean squared error is when you are trying to find, you predicted a number, how far away from the number we're predicting. That would be thinking of the number as 4.7. We said it's 5.2, so we're off by 0.5. It is not mean squared error. Confusion matrix, there's probably a few people that have confusion matrix or something similar. Evaluation metrics, I assume they mean things like this. Accuracy is the same kind of thing. Type 1, type 2, root mean squared error, same as the mean squared error. Confusion matrix, accuracy, this kind of thing. Okay, great. Almost everyone said accuracy. Okay. All right. How close to actual value? That is, again, mean squared error, and that's wrong. Same thing with this. Scores accuracy, root mean squared error. Okay. See, this one is really, you put, like, if you said root mean squared error, sure, you're mixed up. If you said accuracy, you're also wrong for the reason I'm going to say in a second. But if you said both, then you really don't know what these things are, because you would never put these next to each other. You can't do both the root mean squared error and the accuracy. That is like totally different things. Okay, almost everybody said accuracy. This person did the same thing as this person. Okay, this is root mean squared error next to accuracy is so wrong. All right, what is the thing we're doing? So root mean squared error is a good guess. Accuracy is a good guess, but together they don't make any sense. Okay, accuracy is a good idea. Accuracy, which is what almost everybody said, is a good idea. Good idea. And we can tell if we're doing a good job or a bad job with the accuracy. But it is not a good loss function. Not a good loss function. And we talked about a different loss function that is not accuracy, and we talked about why the accuracy is not a good loss function, but let's repeat it here. Why is the accuracy not a good loss function? Yeah.
It doesn't work in the imbalance.
It doesn't work in the what?
When the data is imbalanced.
It does. I think whether or not the data is imbalanced is unrelated to the issue here. So I think I guess what you're pointing out is like if there's a lot of classes where it's imbalanced, the accuracy maybe isn't exactly what you want, right? Like maybe you want to have a different sense of like different types of error, and the accuracy treats all the error types as equal. That's totally true. But that is not the reason that it doesn't make a good loss function. So I think you're right that accuracy has some issues when there's imbalanced data, but that's a different issue than the issue I want to talk about. Okay.
I think you can get good accuracy by just predicting one class.
Yeah, exactly. So that's what he said. So if there's imbalanced data, then the accuracy, you can get like 90% accuracy by just saying, hey, it's that one, which maybe isn't what we want. All right, so that's like the same kind of thing, but it doesn't explain why it's not a good loss function. So when we go to type in the loss function we use is not the accuracy. We do something different, okay? And here's the thing I want you to think about. Think about how is the model improving? How is the model improving? In what way is the model improving? When it was the mean squared error, we were improving the model by making little adjustments to the weights, and the little adjustments to the weights would either increase or decrease the mean squared error, and then we would say move in the direction that improves the mean squared error. Make that mean squared error a little bit smaller. Think about what would happen if you make a small change to the weights. What happens to the accuracy? Maybe I'll write that down. How does accuracy change? How does accuracy change when we make a small change to the weights? Okay. Okay. I will, again, I will open to mathematize so that we get some honest answers from people. Why is the accuracy not a good loss function? And related, what happens to the accuracy when we make tiny changes to the weights? These are related questions, and that is what I want you to think about, so we can learn what's going on here. Okay. Okay, it's open. Okay. Time is up. Put in your guesses. Maybe you have no idea. This one, genuinely, you have no idea. This is more subtle than some of the other things we've been doing. What did people say? Okay. Ooh, I like this word. Differentiable. Differentiable. Okay. It changes, someone wrote, it changes drastically. In fact, the opposite is true. When you make a small change to the weights, the accuracy does not change at all. It does not even move, even one little bit. And that's because, look at what's happening. So the person who wrote changes drastically made a 50-50 gamble on maybe what's going on, and they got it wrong. But look, so suppose we have 3 classes, or okay, let's just do the 10 classes that we have over here, right? Class 1 all the way up to class 9. And we say we are 85% sure that it's a class 1. We think it's 10% of the time it's a class 0, and then like 2% of the time it's class 9. And then we have all these other classes. And then, so we're predicting a class 1, okay? We're predicting class 1. So the accuracy says take the highest thing, right? Take the highest thing, and then you get a point if the true class is 1, and you get like no points otherwise, right? That's what the accuracy says. It says look at the maximum value, and then if you got that right, then you score on the accuracy. If you got that wrong, you don't score on the accuracy, right? The accuracy is a measure of how often you got it correct. Okay, now let's change the weights by a little bit. Now we're gonna do small changes. Small changes. So we change the weights. This goes up by plus 1%. This goes down by 1%. This one goes up by 0.5%. Some of these ones go down, right? We make a small change. We change the weights. The small change in the weights changes the Logits. The small change in the Logits changes the probabilities. We have changed all these probabilities. What happens to the accuracy? Well, what is the top class? This was 85% before. Now it's 84%. It's still the maximum number. The prediction rarely changes, right? The prediction has not changed. Before we were predicting class 1, the probabilities have changed, but now we're still predicting class 1. The only time it would change is if you have a tie, right? So the only exception is ties. So if you had some situation like this where you were like 40% class 0 and 40% class 1, then doing a small plus minus 1% would matter, right? And then you would change the accuracy. So if you have numbers that are very close together, then the accuracy can change. But if you're in this situation, the accuracy will not change, right? You will not be able to tell, is it a better prediction to put 86% or is it a better prediction to put 84%? We don't know. They're all equally good from the point of view of accuracy. Accuracy says all of these things are the same goodness. That is not what we want. And that is the reason why it doesn't work. So some people wrote differentiable. This function, it's super differentiable because it's flat. It's the constant function. The accuracy is kind of doesn't change with small changes in this. So I think some people wrote the opposite things. Not differentiable. So not differentiable means like it has a corner or something. Like it's changing so much, it's changing faster than linear. And this function is the opposite of not differentiable. It's flat, right? It's so differentiable that the derivative doesn't work, right? It's a flat function, the derivative is 0, and you don't gain any information by using the derivative. So it's not that it's not differentiable, it's not changing enough. It might not change. Okay, this is beautiful. This person got it right. Okay, very nice. What else? Okay. No direction for improvement. That is the right kind of idea. Okay. So that's what we got to do. And we did this many weeks ago now. Remember, we're just doing logistic regression. So what loss function do we use? What loss function do we use? And the answer is the cross entropy loss that we learned about a long time ago. Entropy loss. Okay. And the cross entropy loss, it doesn't just take into account the maximum value like the accuracy. It takes into account what was the probability inside the maximum class. You want this to be as close to 100% as you can. So increasing the probability of the correct class gives you a higher score, gives you lower loss. So the cross entropy loss is the one that does this. Here is a little mathematized question, seeing if you remember anything about the cross entropy loss. How do we convert from the probabilities to the cross-entropy loss. So it's the same example as before. We have 3 classes. The probabilities are 0.2, 0.3, and 0.5. And the true label is class 2. So we said 20%, 30%, 50%. And the example we're working on actually is a class 2. It's actually class 2. How much loss do we get in this situation? This is a bit like, it's analogous to the mean squared error because it is a loss function, right? You have a prediction, you have the truth. How far is your prediction from the truth? That's what we're doing. We're combining the truth and the prediction. Okay, think about it. Maybe flip through your notes or whatever you need to do, and let's see how we're doing. All right, 30 seconds left to pick one of these options. All right. Let us see what people said. Haha. Okay. 4 people said this one. This one is the mean squared loss. This is the mean squared loss between the vector 0.2, 0.3, and 0.5 and the vector 0, 1, 0. This is not correct. We're not doing the mean squared loss because we are treating the things as probabilities. So the mean squared loss is like the difference between vectors. These are probabilities. You have to treat them a little bit differently. A good example is the fact that they live between 0 and 1 and not just any real number. So that's not the right answer. The other options are to do either this, minus the log of 0.2 and minus the log of 0.5, or this one to do minus the log of 0.3. To figure out which of these it is, I want you to do a little experiment in your mind. What would happen if we were extremely accurate? Or we were extremely... Let me avoid the word accurate. What would happen if our prediction was extremely good? What would it mean for our program? Right now it's outputting 0.2, 0.3, and 0.5. What would be like the best case scenario? We're like, hey, yeah, this program kicks ass. Look at how well it did on this example. What would the numbers 0.2, 0.3, and 0.5 become if our program was really, really good at classifying? What would we want it to do? What are we like? We're hoping that the program outputs best case scenario. Yeah, okay, that's very good. So the loss function should get very close to 0. That's absolutely right. So we want, when you get it exactly correct, the loss should be 0, just like in the mean squared loss. When you get it exactly correct, you have 0 loss. So that's very good. I was going to ask about that one next. The one I'm asking about now is what should our prediction be? You're telling me what should the output be. I want to know what should the prediction be in that situation, right? If we're predicting these probabilities, the true class is 2. What do we want the computer to do? What are we aiming for? We want the computer to say what?
1 for the right one and 0 for all wrong.
That's exactly right. We would like it to say 0, 1, 0. We would like to say this one, 0% chance it's a class 1. This one, 100% chance it's a class 2, and 0 for class 3. Okay? So if you put in 0, 1, 0, you should have a very low loss, and ideally a loss of 0. Which of these formulas would it have a very low loss if you put in 0, 1, 0? Well, this one, if you put in 0, 1, 0, the 0.2 becomes a 0, the 0.5 becomes a 0. What is the log of 0? Log of 0. The log of 0 is infinity. Well, negative the log of 0 is infinity. So actually in this one, if you put in the exact right answer, the best possible situation, you put in infinite loss. That's not good. That's the wrong answer. This is the right answer. And when this goes up to 100%, you have minus the log of 1. The log of 1 is 0, and you have 0 loss. So this one is the right answer. 9 people got it. So what is that? Just under half the class? Yeah. It is minus the log of the true class. That is the right answer. And you might remember this formula, right? It's the sum of the, let's write it this way. So in the example we did before, you could write it like this: 0 times the log of 0.2 plus 1 times the log of 0.3 plus 0 times the log of 0.5. So in other words, you do zeros for the classes it's not, you do ones for the classes it is. Oh yeah, this is the log likelihood. Remember, the cross-entropy loss is negative that. And then you add them up. In general, you can write it like this: the sum, and then you can do the indicator function of example true class for the example is class I. So it's either a 1 or a 0, and then you pick up the log of the p hat exactly on the one you're on. So you sum over the number of classes. So that is the cross-entropy loss. Don't forget the negative sign, or your program will do the opposite. And this is when we talked about logistic regression. This is the loss function that was used. And we talked about where it came from. It came from the Bernoulli random variables from coin flips. This is the log likelihood of the coin flip coming out a certain way. Okay, this was the log likelihood. Okay, fantastic. So let's put this in our computer program now. So our computer program is here. And we have to fill in the cross-entropy loss. We have the parameters. Those are the weights and the biases that we're using. We have the images. Those are the pixels of the images. And we have the target. That is the true label that we want. We've computed the prediction by doing the log p function we did before on using the parameters and the images. Now I have something called target as a vector. So the target right now is a number. It's saying 1 or 2 or 3. What are you, right? It was exactly what we were printing out like way back up here. Right? So the target is a number like 9, but I want to turn the target into a vector by doing the one-hot encoding. So we're going to turn it into a vector by doing the one-hot encoding, just like we had in our formula. Okay, we'll go all the way back down to here. So the formula, and I believe the function, I think it's JNN. Oh, look at that. JAX.NN, that stands for JAX is the package we're using. NN stands for neural networks, and one-hot encoding says turn it into a one-hot vector, a vector of size 10, 0 to 9, and there are 10 possible classes. So Google is reading my comment and then using the comments to figure out what I need to do, which is quite nice. Let me also make sure Google didn't make a mistake, because sometimes it does. You've got to be careful with these things and sanity check them religiously. What did it do? Okay, no, in this case it's correct. Okay, very nice. And so what is the cross-entropy loss? It is the sum of the target as a vector. So jnp.sum I want of the predictions times the target as a vector. And actually, let me write it the other way so that it matches the formula I wrote on the board. This times this. Okay, that is the sum. Very often, instead of doing the sum, you want to do the mean so that the whole thing doesn't get bigger and bigger, and that's the average cross-entropy loss. Okay, that's very nice. And then is this what we want? Yes, okay, this is perfect. So there we go, we just put in that formula. Now I run it, and here I have my predictions, and now it's actually calculating the cross-entropy loss, and says the cross-entropy loss is 4.43. Now we run our thing, and we say, please do the training loop. Remember, the training loop inputs the function, and it inputs the cross-entry loss. And it says, try to make the cross-entry loss smaller by gradient descent. So I'm going to start running this, and then I'll write what it is again, so it's running. And remember, we minimize, so change weights in the direction of the gradient to minimize the CE loss. So we make the cross-entry loss as small as possible by doing little changes to the weights to try to shrink it down. And you'll notice, like when you shrink it down, right, in a situation like this, we're getting penalized by the log of this number, so we want to make this as close to 100% as we can, right? That's exactly what it's doing. So you got the sense of that in the example we did. Let's see how it did. Okay, so this time, okay, maybe I have to let's try it one more time. Let's see what happened. I'm doing the accuracy. The accuracy needs to be filled in. Why am I doing the accuracy? So the accuracy is not good for training it, but the accuracy is good for figuring out how much you're improving. So it's a little bit hard to interpret. What does a cross-entry loss of 1.2 mean? You can figure out what it means roughly, but it's a little bit easier to also get the predicted classes and then use the accuracy, which is, I call it the top one accuracy. It's how often the maximum thing got it right. And so that is, I think, the argmax function. Yeah, okay, there we go. So the argmax, is that the right thing? Google is so good these days. Maybe it's copying from my other file. Maybe it knows that the two files have to be linked. So it's saying, find the class that has the largest probability and return that one. And if that is exactly equal to what it was supposed to be, then we're happy. So okay, we'll run it again, and we will now see the accuracies going up, as well as the cross-entry loss going down. Hopefully, fingers crossed. You never know with these things. There's no guarantee. You gotta run it and try. And if something is slightly wrong, nothing will work. Okay, so our accuracy started out. Our training accuracy was 87%. Our test accuracy on the validation set was also 87%. So that's pretty good. We're not overfitting. Our cross-entry loss was like 1.26, 1.28. And then we fed it all the examples. We trained it again. And our accuracy went down. Oh, no. It was 87% before. Now it's 85%. So probably maybe our step size is too big. Let me make our step size a little bit smaller and try to run it again. This time, let me not... Actually, let's just reinitialize everything. Let's run the whole thing and see if we can do any better. When I ran it, how did I have some results here from when I ran it the other day. Okay. And this is the logistic regression. Logistic regression, okay. Okay. Did it improve? Okay, this time it improved. Look, it went from 86.5% to 86.9%. It went up just a little bit. Let me not spend hours and hours doing it. Let me just show you the results I did earlier. Here I ran it earlier, and I got all the way up to 89%. So we did it a few more times. You run it for longer. You feed in the data over and over again. You do these small improvements, and eventually you get something. This is like 88, 89% accurate. In this situation, these are what the predictions look like, which is quite nice. So you can see if it's working or not by outputting some individual predictions. Oh no, is it going to have to run everything again? Yeah, okay. Let's run everything again on this one. Let's see what the predictions for this one look like. So this is just saying, draw some pictures and do our predictions. So this was this image, all the pixels. Our logistic regression thinks it's a 0. All the pixels over here, our logistic regression thinks it's a 4. Hey, that's pretty good. That's a lot better than it was before. Hey, look, we got all 4 of these right. I mean, we get like 80% of them right. So the odds of getting 4 in a row right is pretty good. Amazing. Okay, so far, we have done nothing new. We have done all things we have done earlier in the course. We did linear regression, then we did logistic regression. We just did it by hand from scratch, right? And you have to understand all the details, because otherwise, what do you type in the computer? So far, we've done nothing new. The next thing we're going to do is do this thing called the multi-layer perceptron, trained with cross-entry loss. And all of the stuff we've been doing up until now has just been sort of warming us up for all these ideas. Now you really know what the cross-entry loss means, and you know we're going to see how to make it multi-layered. We're going to do that in 1 second. Any questions or comments about this thing before we go? So far, it's just implementing logistic regression. Okay, so what is the idea of a multi-layer perceptron? The word multi-layer should tell you what to do. We're going to repeat exactly what we did. So we're going to do this cross-entry loss. We're going to have 10 output categories. We're going to do this picture. What are we going to do? We're just going to add more layers. Add more layers. That's all we're going to do. So let me, because it's a digital backboard, I can steal the input. I can drag the input over here. Oh no, the neuron. Go back, Mr. Neuron. Go back. You don't run away from me. Okay, you stay over there. And then we're going to add new neurons. So we're going to make these, I guess these should be purple too. Okay. Purple? Okay. X2. And we're going to add another layer in between. So the input, instead of being over here, right, the input is all the way over there. And then we just like sneak in another layer. So we add more weights. This thing is called a hidden layer. The hidden layer. Okay. And by adding a hidden layer, so instead of the weights being 784 by 10, the 784 by 10 is the weights of the last layer. This is called layer 1, and this is layer 0. And layer 0, it'll be 784. Actually, let's call it 784 by hidden. And the weights we had before were hidden by 10. So in other words, we're just adding a layer of computation. Instead of taking the input and directly getting the output, we have this intermediate layer. So we do these linear operations, then we do them again. And by doing lots of linear operations, you can let the computer do even more weights. So the number of weights is much, much bigger than it was before. And that can let it do more computation. So the thing we have to decide is how big we want to make the hidden layer. And it is up to us. We can make it very big. We can make it very small. Sometimes you want to do one or the other. A not bad rule of thumb is to maybe make it around the same size as the 784. Let's see. What did I do? What did I do when I did it before? Let's make it the same. I think I made it exactly 784. So why don't we do that? So I'm going to set the hidden layer to 784. And we're going to do this computation and then crunch it into the classes, just like we did before. OK. Let's go here. So the layer sizes, I'm going to do 784 by 784 by 10. And the middle 784, this is the input, has to be 784. This is the output, has to be 10. But it is totally up to you what to put in there. Some could be good, some could be bad. It's hard to know without trying. OK, then I have this function called MLP, which stands for multi-layer perceptron. And it's going to output the log probabilities just like we did before, right? So exactly the same way of doing the x's. We just have to do the first layer. And the first layer takes the image, and it outputs this thing called x. Right now, x is the image. And we're going to do exactly the thing we did before. We're going to do the dot product like that, wx plus b. And let me make sure. I don't want a 0 or something. OK, yeah, wx plus b. That's exactly what we were doing before. That's saying do one layer of computation. Now, because the weight w is a 784 by itself, x is already, it's a vector. There is this thing called x transformed. Let's ignore that for now and see what happens if we don't use that. We will be back soon with that. But here is the x, and I'm just going to update x. I'm going to just apply the same function again. So just do the same thing one more time. And I do JNP dot wx plus b. OK, so I'm just applying this function, the dot product of w and x plus b, over and over again. That is the same thing as saying just do the calculation in the picture over and over again. Let's go all the way back to when we were doing linear regression, right? Dot product calculates the next thing. If w is a matrix instead of just a vector, the dot product will calculate it for every single entry. We're adding on the b to every single entry. So we're just doing this function over and over again. And this is the whole thing. We just do it multiple times. That's the whole thing. OK. All right. Then we have the final weights and the final bias. This is the very last layer. And the very last layer is important because that's where we convert into logits. So the logits will be what you think. So JNP dot final w comma x plus the final b. And then I'm doing the maximum trick again. And the log p is exactly the same formula as before. It's the logits minus the log sum x of the logits. OK, and I want the max to 0. Thank you for reminding me, Mr. Google. OK. And that should work perfectly well. OK, let's run this and see. OK. See what happens. Okay, so now it is outputting the thing. We're going to train it. Again, here we batch it like before to run on all the examples at once. The loss function is exactly the same as before. And now I have the whole thing, top 1 accuracy. I'm running it again. Remember, before we were doing it purely with logistic regression, and we got like, how good did we get? We got like close to 90% accuracy. So before it was 90% accuracy. Then we added more layers, and let's see what the accuracy goes up to. This is a good place to stop while we're waiting. We're waiting for it to train. You'll notice it's a little bit slower, and the reason it's a little bit slower is there's more layers of computation. It has to do more work. Every time it does a derivative, there's twice as many variables. So it's the more parameters you add, the slower it goes. And we're trying to figure out what's going on. So the accuracy is like 84% here, and it's slowly going up. Any questions or comments so far? Okay, let's see what the accuracy got up to. Got up to 86%. Let's run it for longer. So if I delete this line that is initializing it, I can run it for even longer, and it'll just keep improving. So it was 86%. Let's see, is it getting a lot better than it was for the logistic regression? Yes, I suppose at this point in time, you can wonder, how much better is it going to get? Adding 1 layer, does that help a lot? 87%, that's about the same. Let's see, if we do even more, is it going to get even better? Okay, 87.8%. This thing is doing the exact same goodness as it was before with 1 layer. We added all these extra layers, and it turns out we're not doing any better. We added more layers, but it did not improve. And if you've taken a linear algebra class, you might have a suspicion of what's going on. So observations, more layers, specifically 1 more layer, on its own, did not help. And one way to see what we did is we were doing matrix multiplication. So before, we had W1, the matrix of all the W's, times the X's plus the B's. And then after, we had 2 layers. So we were doing W2 times W1 times X plus B plus B1 plus B2. Okay, let's get rid of the W1. So in other words, before we were just doing WX plus B once, and then afterwards we were doing it twice. So we were taking the output WX plus B, and then we were doing it again. But what happens if you have a matrix and you multiply by another matrix? You're just doing, just by like the most basic algebra, you're doing W2 W1 times X plus W2 B1 plus B2. Okay, and if you just call this thing B, and you call the product of these 2 matrices W2 times W1 W, we're actually doing the exact same thing we were doing before, right? If you apply linear operations over and over again, you don't get something new. You just get a different way of parameterizing your linear operations. So we sort of have a really complicated system of equations, W2 and W1, but they get combined together to give 1 matrix W, and we're not actually doing anything different. That's why it's not getting any better. We actually have not done anything. We've added a layer. It's made the computation harder, but it's not changing the set of functions we can represent. It's still doing linear. This is still linear. Still linear. So in other words, a product of 2 linear things, doing a linear thing over and over again, you're still linear, right? You have not escaped the set of linear things. And that is why it's not getting any better. We could stop there and just say, okay, I guess it doesn't work. Let's give up. But it turns out there's like a really small, just like the world's smallest little tweak that you can do to break free, break the chains, and escape the land of linear. And then you go into the land of nonlinear. And once you have entered the land of nonlinear, things really can get dramatically better.
Can I adjust the weights?
Unfortunately, adjusting the weights will not work. So if you adjust the weights, you just get a different matrix W. So you can't just adjust the weights. This is the problem. No matter how you change the weights, as if you're doing linear, 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 no matter how you do it to the weights, it will still be linear. This is the problem. So we have to do something else. And all we have to do is, so this was after, this is the after, but let me put in the, with the modification, Okay, let me actually just write a new one because I think this will get confusing if I try to do this. So, so we have W2 times W1 plus B plus B2. This is what we're kind of doing. And the problem is the W2 and the W1, they just multiply each other. So the only thing you have to do to make this better is just insert a little function right here. Let's call it f for function, for some nonlinear function f. So as long as you apply a nonlinear function in between these layers, that will break the product. Now you cannot do W2 times W1 because it's not linear. You see, you do this nonlinear thing to this, and then the W2 gets applied to the nonlinear guy. And now it is not the same functions anymore. And this little tweak is like a huge difference. So you break out of the land of linear functions, y equals mx plus b, and you move into the land of nonlinear functions. But somehow it's 90% the same. Like from the point of view of the computer, all the work is the same. It's just that we've added this function in exactly the right place to make the things do what we want to do. And in our code, it's extremely easy to add. All you got to do is update very slightly the code. So I have this function called ReLU. This is the function I'm going to use. And the formula for ReLU is very simple. It is the maximum of 0 and 1. How did I implement it, actually? Yeah, the maximum of 0 and x. So it's the nonlinear function. It's called the ReLU function. And it looks like this. So here's the function f I'm going to use. F of x equals the ReLU of x. ReLU stands for rectified linear unit. But it's kind of a funny name. It's this function. It's like that. So it's 0 if x is less than 0, and then it's x if x is bigger than 0. And you can write this very compactly as the maximum. So if x is bigger, it's x, and if 0 is bigger, then it's 0. Okay, very nice. And we just apply this function in the hidden layers of our network. So before feeding, after we do one computation, before we go into the next layer, we transform it by applying ReLU. So we just do ReLU of x. Oh, and I misclicked to run it before the bracket was there. Very good. Okay. And let me make sure I'm not missing something. Okay, and then I will, x transformed, I will do ReLU of x. Okay, there's one small bug in this line. Does anyone see the bug? It would be very tempting to run it now and be like, great, I added it in. But what's the bug in this line? Yeah. No, the bias is okay. Yeah. This is the kind of thing you can stare at this for hours and be like, yeah, x, and then I transformed it, and then I apply the next layer, and then I transform it, and then I apply the next layer, and then I transform it. It's working. But I did something very dumb. So here it says jmp.wx plus b. Which line is it going to take from? X equals this thing. X transformed equals the ReLU applied to x.
You need to use your transform.
Exactly. I made the transform variable and then I never used it. Okay, very good. Yeah. Okay. X transform. Okay, so you got to do that. Of course, sometimes the way people do it is they make this line say x equals ReLU of x to save themselves a little hassle, but I think this is better. Okay, and then do I have to do the same thing over here? Over here, same idea. Should be x transformed. So in practice, you'd probably just say x equals, but this way you can see more explicitly where the f is. Okay, and there we go. These are the Logits is opening, and now hopefully it will work better. Let's see. Oh, the syntax error. What? Oh, I see. I put a comma. Okay, very good. Thank you. Okay. Cross entropy loss. Very good. All right, now fingers crossed it works better, because otherwise I'll be very embarrassed. Okay, it's training. Big money. Let's go. What did I get when I did it last time? Okay. Remember, before it was like 86%. Then we added in these ReLUs. What is it going to be? Is it going to be like 90%? Is it going to be like 91%? Let's see. Come on. Ha! 95% accuracy. Woo! We did it. All right. Celebrate. See you guys later. No, okay. That's it. Okay, that's the whole thing. This is the magic that has powered that has powered the AI revolution. Is you add in this one dopey function, and suddenly you go from like 86% accuracy, which is like 14% error, to 97% accuracy, which is 3% error. It got 5 times better. The error got shrunk by a factor of 5 just by adding in that one stupid function. So now it is amazingly accurate. By the way, this is about as accurate as humans are. If you ask humans, you give them this data set and you say, please label them. Humans also got around 98% accuracy. So suddenly, it's already like human accuracy. And actually, this is a good way to see how accurate we are. We're making 3% error. What are the ones that we're making mistakes on? And that's right here at the bottom. These are the digits we're getting wrong, okay? This one, we thought it was a 0. It's actually a 9. I would say that's an 8. Like if you asked me to label that, I would say that's an 8. This one, we thought it was a 1. That's a 5. We made a mistake. Sorry, guys. I would also say that's a 1. This one, we said it was a 9. Apparently, that's a 7. So the ones we're getting wrong are the really messed up ones, right? When people write things on paper, they will sometimes write stupid things. Look at this guy. This is like a Cthulhu or something. Okay. We said this one is a 1. It's actually a 2. So we got that wrong. We were wrong. This one, we said is a 9. It's actually a 7. So the ones, the computer is so accurate already, which this 2-layer network, just by adding in the F, that the only ones it's getting wrong are the ones that any reasonable person would get wrong. So even though the error rate is like, it's accurate, its accuracy is like 98%, its error rate is like 2 or 3%, the ones it's getting wrong are the really, really hard ones that like you should expect it to get them wrong because they're kind of silly. So it's doing a great job. Okay, here are some more. Okay, some of these are pretty reasonable. Like this was an 8. We said it was a 3. Like we should have probably got that one. So you know, like there's some room for improvement. I'm not saying it's perfect, but it's extremely accurate compared to the previous methods. Okay, so that is the summary of everything we've done here with the neural networks. And I wanted to show you like how it actually works in the code and how it really is almost exactly what we've been doing in the course, right? Like what did we have to change? We had to take logistic regression. We had to make 2 small changes. All we had to do was add a layer. Let me see, was there a picture? Yeah, I had a cool picture. All we had to do was add a layer, and then we also added a function f. So let me add that to the picture. We had to add a function f that goes around every single thing before it gets sent, right? We have this nonlinear function f called the ReLU function. Apply the nonlinear function, nonlin, f of x equals ReLU of x between layers. And that made a huge difference. Okay, so that was easy. The actual hard part of the network is the stuff you guys have been doing the whole term, which is like, why are there classes? What is accuracy? Why is accuracy different than like the cross-entropy loss? What is the loss function? What does it mean to convert the probabilities into the loss? Like these are the hard questions. That's the hard part of doing this. And we've done that the whole term. The easy part is adding more layers and like applying f. That part is easy. So we've sort of like built up, even though in the class we've been doing these very traditional methods, it should build the foundation for you to learn this kind of stuff, if that's what you're into. So this is, if you want to do a model like this for your final project, this is a really great one. And I know it's like quite hard and time consuming to get these networks working, and I will take that into account when I'm grading. So it could be a fun one. If you want to learn neural networks for your final project, you could try something like this. That actually, if that would be a good one. I said the student scores is a little bit easier of a data set, but if you're like, I'm going to do student scores, but I'm going to do a neural network from scratch, that's like a valid project. I would grade that quite highly because I know it's quite hard to get the code working well. Okay, we have 1 more minute here for questions. Any questions or comments about any of this stuff? Yeah.
Why ReLU function? Why not other functions?
Oh, why the ReLU and not other ones? The ReLU is really easy to compute. So you remember we're doing the gradient, right? And the gradient of the ReLU is a super simple function. So this is the ReLU. Let's do the derivative of the ReLU, f prime of x. The derivative of the ReLU equals, it's this function. It's 0, and then it's 1. So this is the derivative of the ReLU. So the derivative of the ReLU is very, very simple, and that means it's very efficient when it runs in the computer. And the computer has to take the gradient. It's doing that step very quickly. Of course, you could use any other function. Like you could use another common one is the tanh function, the hyperbolic tanh. Many functions will work and get sort of equivalent answers. The ReLU is a really common choice because it's highly efficient computationally, and it seems to work as well as many of the others. If you learn a lot about neural networks, there's a lot of like lore about, oh, in this situation you use this one, in this situation you use that one. But fundamentally, my understanding is nobody really knows anything, so they're just making stuff up. People have tried different things, and they see what works and what doesn't work. Yeah, great question. Anyone else?
So is the accuracy going to be better if we have more layers?
The accuracy could become better if you have more layers, depending on the problem. In this particular problem of the MNIST, getting to like 98 or 99% accuracy is about as high as you can get, even if you add more layers. You should think of adding more layers is equivalent to sort of adding more parameters, right? And we've seen before that if you add more layers, you can start to overfit. So you got to be careful. But it kind of, again, nobody understands really why, but neural networks tend not to overfit very much. So probably what would happen if I added more layers, I would get the same accuracy, but it would take longer to train. It would take a lot longer. The more you add, the more computation it has to do. It would take longer to train. On a very complicated data set, adding more layers can help a lot. If your goal is to do the English language and output like what humans write on the internet, then making a model, instead of having thousands of parameters like the one we did, if it has billions and trillions of parameters like ChatGPT, then it actually does improve the performance. So making it bigger and adding more layers can help, depending on how hard the problem is. Also have to be careful that it doesn't overfit, but in real life that tends to not be an issue for miracle reasons that nobody knows. Yeah, great question. Was there one here? Yeah.
Yeah, after we added the function,
Yeah.
that was when we got the accuracy, the increased accuracy.
Yeah.
So I was thinking, should we have actually added another layer? Because it didn't really improve anything, right?
Yes. So that's right. So if you add another layer, oh, you mean before we, instead of the function, if we added.
No, just use the function instead of the second layer.
I see. Okay. Yeah. Okay. This is absolutely fantabulous question. Let's do this. So we started with linear, and then we said let's do 2 layers of linear. And your suggestion is, what if we do 3 layers of linear? Is that right?
No.
Okay.
Linear and the function.
Oh, just the function.
Yeah.
Okay. Well, that's what we did. That was the example we did. That was all the way up here. With the, do you remember we were doing it as when we did this, the 9 times the sigmoid. Where is this? Somewhere here. Okay, wait, let's go to the thing. I have it labeled. The linear regression, non-linear. There's this one, non-linear but still regression. And this one we were applying a function right at the end. And so the problem with applying a function right at the end is like you've already baked in what your predictions are. You're just like messing with them. So this is, I think, the secret sauce is that you're applying the function to the hidden layer. And the hidden layer is some kind of like high dimensional representation of the function, of the image. Like, does it have a round top? Does it have a bottom? And by applying a nonlinear there, then you can gain a lot of leverage that will then apply to the probabilities. So in other words, by the time you've created probabilities, it's too late to change things meaningfully. You want to change things before you get to the final layer. Yeah. Yeah, great question though. And again, like a lot of this stuff, everything we've done in the course like has been like traditional stats, like linear regression, logistic regression are really well studied. There's a lot of theorems. People have spent a lot of time on it. All this neural network stuff is new in the age of fast computers. So like nobody knew any of this stuff like 20 or 30 years ago because computers were not fast enough to try things out. So a lot of the things that are known about neural networks are just known by experiments. I ran it this way, I got this. I ran it this way, I got that. People don't have the same theoretical understanding that they do for the other models, and a lot of the stuff is by sort of trial and error. So like it could be, you could come up with some wacky thing. You're like, I add a function here and I do this, and like, does that work better? I'm like, well, maybe, I don't know, try it and see. It could be, yeah. Great question. Okay,